This section is about choosing coordinates, defining extension, and identifying forces. For students, this is usually the first time they see how mathematics and physics talk to each other. Let's enrich the explanation with more facts, clarity, and a real-life application. 1. Defining the position. We let z of t represent the vertical position of the mass at time t, measured downwards from the top fixed support. If the spring is exactly at its natural, unstretched length, then the mass is at z equals L. 2. Defining the extension. The extension of the spring is the extra amount the spring is stretched beyond its natural length. Text, extension equals z minus L. If z or L, the spring is stretched. If z L, the spring would be mathematically compressed. For an ordinary hanging spring, compression rarely occurs unless an external upward force is applied. 3. Forces acting on the mass, weight, mg's, always acts downward, and in our sign convention, downward equals positive, it is plus mg. Spring force, K(ZL). By Hooke's law, the restoring force is proportional to the extension but always opposes displacement. If the spring is stretched, zebra L, the spring pulls upward, negative sign. If the spring is compressed, zeta L, the spring pushes downward, still consistent with the sign convention. This balance of forces is what leads us to Newton's second law and the equation of motion. Extra facts for students. The choice of coordinate z measured downward is not unique. We could have chosen upward positive. What matters is being consistent with the signs of forces. The definition of extension, ZL, is crucial because the spring only cares about how far it is stretched or compressed compared to its natural length. Hooke's law is linear, F equals minus kx, only for small extensions. Real springs may behave nonlinearly if stretched too far. 1. Newton's second law and equation of motion. From the free body diagram, m.z, L. The left-hand side, m.z, is the net force, mass acceleration. The right-hand side has two forces, the weight mg pulling downward and the spring restoring force, K(L) pulling upward. Fact, a good habit is to always check the units. Every term here is measured in newtons n. mg is in n since m and kg and m such as squared. K(L) is in n since n m's extension in m. Emma.z is in n since kg m squared equals n. This consistency reassures us the equation is physically correct. Hammerscher 2, static equilibrium position at rest, .z equals 0, so the weight is balanced by the spring force. 0 equals mg minus k at text eq minus L, quad, long right arrow, equals L plus frac mgk. This means the spring stretches an extra distance. Delta equals frac mgk. Fact, this tells the static deflection. It shows that gravity simply shifts the equilibrium point. It does not change the nature of the motion. 3. Displacement from equilibrium. To simplify, define y at t equals z at t minus z text equal so that y equals 0 represents the equilibrium position. Substituting into the original equation cancels the constant terms, leaving m dot y plus ky equals 0. This is the classic simple harmonic oscillator SHO equation.
We share.
Tutorial questions and answers.
It is all about understanding facts and sharing with others.
Learning continues. We are learning to know, understand, and share with others.
Please subscribe to our channel if you like our videos.